Okay, last week we talked about the EFA and we covered these topics. Okay, number of vectors, we just use some four methods to decide the K number of vectors. And then to run the estimations, we have the eigen decomposition method, and we also have the maximum likelihood estimation method. Factor rotations, we introduced some rotation methods, and the factor scores, we have two ways to get those scores. How are we going to do the interpretations? So today we're gonna continue the lab. So we didn't have time to finish the lab of the EFA. So we're gonna continue the lab today to see the details of these topics. Yeah, so that's the first session of today's talk. And then we're gonna move forward to CFA. Okay, CFA. It's kind of like related, but it's different. So how are we going to conduct CFA? How are we going to do the model identification? And also we're gonna look at the model evaluation to see if the model fits the data well or not. Actually, we have already covered this part last semester. We are going to use those criteria, okay, fit in practice on this topic. And we have a new package. Okay, so we are going to use a new package in R. It's called Lavan. Okay, it's quite similar quite similar to M+ code, but it's very flexible. It's very powerful. Okay, and we will have the code and do the exercise. Okay. So first session, let's go back to the EFA. So EFA, we haven't finished the lab part. We stopped here, and let's have a very quick review. So we use this example. In total, we have 19 tests trying to measure these four latent abilities. So these four are latent abilities. By running EFA, we're gonna figure out these four abilities. And the sample size of 145, they are from the GW school, okay, GW school. So this is the introduction of the theoretical framework, the background of the cognitive ability. So we have four tests which gonna measure the spatial ability, and we have 5 tests which are influenced by the verbal ability, and we have 4 tests gonna measure the speed ability. We have 6 tests which gonna measure the memory ability. Okay. And that's the R code. So everyone should download the R code from our website of the last week's folder. And so we trying to explain part of the code. I think we have already explained it. So let's just go to the R Studio, and then you have your data file ready. So it's called housing.txt. So it's available in our ELC. So download that website, download that file and save it to your local folder, and then you're gonna set your working directly. So click session, and then click set working directly, and choose directly. You're gonna choose your home or working directory. So suppose in my case, it's saved here. So you should have your own folder. So that's it. And then you're gonna use a very powerful function called read table in R to reading the text file into our R, and we're gonna call it housing in our R code. Okay, this is the original data set. It's a huge data set. Include a lot of columns. If you go to the data file, so that's it. So we have a lot of tests, and also we have some other ID or gender information. So you can just try to look at the original data format by using the head, okay, by looking at the first 6 rows of the record. That's it. That's it. And then we're gonna pick some tests, 19 tests specifically. We're gonna pick 19 tests from the original huge data set. Do the EFA. So these are 19 tests. Okay, so these are 19 tests. And by using the selecting columns from a matrix data set, okay, we use a bracket and input the names of these columns. So these names, this is defined here. So these columns should be chosen. And we're going to save it to another data file called FA, Fact Analysis Data. So this is a smaller data set. This is just only subset of the original housing raw data. So you can also use the head function to check the simplified or smaller subset of the original one. So you can highlight these 3 rows and click run. So these are much smaller sample size. And of course, you can check the sample size. Okay, n row. How many rows? So it is a sample size. And column. How many columns? This is the number of columns to check the data file. So we have 19 columns, 19 tests. We have 145 samples, okay, data observations, so this is sample size. Okay, so everything seems ready. So now we have our data ready. We are going to use the eigen decomposition to do the data analysis. This is a function, but after eigen, the information inside the parentheses should be a matrix. We are going to do the matrix decomposition. So what is this matrix? It can be covariance, but usually for EFA, we use a correlation matrix. How are we going to get the correlation matrix? COR is a function to obtain the correlation matrix. Okay, COR of this sub data set. Okay, the small data set. So this correlation matrix is 19 by 19. We have 19 variables. In total, this is a huge data set. It's 19 by 19. Okay? This one gonna run the eigen decomposition, and we save everything, the result here. So called fact analysis eigen. So let's try to run the correlation, and you can also type in this, print the correlation to check the huge 19 by 19 matrix. That's it. Okay, this is our matrix. Okay, so we have 19 columns, 19 rows, and the diagonal elements are 1, 1, 1, 1, 1. Okay, because it's correlation. And the off-diagonal elements, all of these are correlations among different tests. For example, the correlation between visual and the cubes, okay, it's 0.3, 0.3257. Okay, so the correlation between visual test and the paper is this number. Okay, so all of these correlations are listed here. And that is our matrix. So just run eigen. So the R code will do the eigen decomposition for us. So run this function, and then we're gonna check what's inside in the result. Actually, they include 2 parts: eigenvalues and eigen decomposition, eigen vectors. So we have values, we have vectors. So we can use a dollar sign to pick the specific objects inside the result. Are you going to look at values or vectors? So we can use dollar sign to look at these results. Because the dimension is 19, so we should have 19 values. Okay, 19 eigenvalues. That's it. from the first one, the biggest one, to the smallest one. This is the smallest one, 19. Also, look at the eigenvectors. So eigenvector and eigenvalues are one corresponding. So we have the biggest one. So the first column is the eigenvector corresponding to the this eigenvalue. So the chances. Each column is just one eigenvector. Okay, so we have the first column corresponding to the first eigenvalue 6.6. The second column corresponding to the second eigenvalue based on some time. Okay, so I have this is just our view pages, and get off and the translation is very experience. That's our matrix. Okay, so that's the position, the middle matrix. Okay, this is the result. And this is the subject, which is side up, side here. So we have function, she just write highlight the full function, so you want to highlight full function here. So from the function to end of function, from the beginning of the function to the end of function. So this is all just go from here on inside the direction of the function. It's a little bit. So first, do the decomposition of original data. Okay, the correlation matrix of the original data include decomposition, which we call the values. Those are original eigenvalues. We're gonna compare those values with some generated noise eigenvalues. If these original eigenvalues are larger than the noise generated, okay, it's kind of like the noise eigenvalues, we think that these eigenvalues could due to some specific reason, okay, factors. So we pick that number as our K. So we have the original sample size, not sample size, original matrix, okay, n row, p columns, and we create empty eigenvalue matrix. And we have loop, okay, we have for loop. From 1 to R, the R is the input information. You can make it very large. And it's kind of like a repeated procedure. So we have randomly generated normal distributed numbers. Okay, this is a sample size and this is a dimension. So we put them in the array and we calculate the correlation matrix of the newly generated data set. We do the decomposition and we got the values and we just save it by using the R bind. Okay, we just every time we have a new row bind, R bind. So every time we have new row information added to input this matrix. Okay, PA eigen. Originally it's empty. Now means empty. But starting from 1, 2, 3, 4. Okay, finally you will have R rows inside of this matrix. Okay, all of these informations are eigenvalues. So basically we have all rows of eigenvalues. And then we're gonna use the apply function to calculate the mean of what? Okay, columns of these eigenvalues. Okay, so huge matrix. So it's all rows, usually 1,000 or 2,000 rows. And here we have some numbers. 1 means we're gonna calculate a row means. 2 means I'm gonna calculate the column means. So column means which are saved inside this average or mean eigenvalue. We can also calculate the quantiles of different eigenvalues. So this is not mean anymore. This is just quantile. And what's the probability percent of the quantile? It's decided by the information we input. 95% or 90% or 80%, okay, you can just change this information. Once you decide this number, so the information will be used here. We're gonna do the quantile calculation and everything will be saved here. And we're gonna plot the eigenvalues. Okay, original eigenvalues will be plotted like this, and we add some lines. This line is for the average mean. This line for the percentile. We have different types of this line. Okay, 3 or 2 or 1. So this means different types of our these lines. Okay, solid or dashed or dotted. Sometimes we can also add a color. Okay, color equals green or red or blue. Okay, black. So you can add those information here. And we have some legend here, tell the readers the information of the data. Yeah, so after we run the function, so that tells us this function is ready for us to use. This function, it's ready for us to run the parallel analysis. You only needed to input this information. What's your original data? What's the repeat number? What's a percentile? So percentage number. So when you want to run, if you want to run this code, you can only run the name of this function. It's called call or function. Call the function. And then what's the information? The factor analysis data or FA data is your information. Okay, the 19 tests are input here. 1,000 repeated times, okay? This is your repetition. Percentile, I'm gonna calculate the 95 percentile upbound. That's information. So after you run the command here, click run. That's it. This is our plot. We have original data plot, eigenvalue plot, and we have 2 lines. Okay, 2 lines, one for mean, one for percentile, 95 percentile. So you can do the comparison. So to see if this original eigenvalue is larger than this 2 line or not. Okay, you're gonna use the average line or upper bound. It's up to you. Usually, if you use the average line, you have 4 values larger than this line. If you use upper bound, still you have 4. Okay, so this is very close to the upper bound. So you can decide the case. 4. So suppose it's 4. Then next, you can do a lot of data analysis. You can run factor analysis. This is short for factor model with analysis. It's a function built-in, and there are replacement package. Okay, so we have the original data, so factor data. Now you need to tell the factor analysis function how many factors you are going to use. I said 4 based on the previous analysis. Okay, 4. And then you can, by default, there's no rotation method, no rotation. Okay, Of course, if you use none, it's the same by default. Okay, and then you can try to look at the result. Okay, so highlight this part, click on. And the result is quite simple. If you want to look at more result, you can use a summary. Okay, so this is the original. Yeah, call this function. And this provides a uniqueness. Okay, varies of the uniqueness. Okay, so we have common vectors, we have unique vectors, and we have loadings. Okay, this is a loading. This is a lambda matrix for 4 factors. Factor 1, 2, 3, 4. So this is a huge lambda matrix. So we have 19 tests here. So it is K by N. Okay, so I'm sorry, it's P by N. P. I'm sorry, it's I'm sorry. This is a P. Okay, number of variables P by K. This is not N. Okay, not sample size. This is K. Number of factors. So P by K. P 19 tests. K 4 factors. And look at some space here. It looks like 0. But actually, these are not 0. These are tiny numbers. So R, by default, just delete those tiny numbers because they think, okay, these loadings will not gonna influence on the result. So although this shows blank, actually there are some 0 point, maybe 0, 1, 1, 1, okay, or 0, 0 something, some numbers here. So it shows us the vector loading, the matrix, it's just like this. If we do not run any rotations, this is original lambda matrix. So you can tell that some values are very large. Okay, for example, here it's almost 0.6. This is 0.7, 0.7. And look at this. Okay, add. Okay, so we have here 0.455, 0.475, the negative 0.45. So you can see that this lambda, this tells us, okay, the add variable is influenced by factor 1 by using this coefficient, influenced by factor 2, with this coefficient, influenced by this factor 3, with this coefficient. The pattern actually is not very clear, but this is good. Okay, so word C is influenced only by the factor 1. So these factor loadings are quite small. So small you can ignore it. This is good. We try to find a much clearer pattern. Okay, so of course sometimes you can decide to delete this loading because it's only 0.1. Okay? But even you deleted this one, you still have these twos quite large. Code is influenced by factor 1 and influenced by factor 2. It's not good pattern. Okay, so then we're gonna do some rotations. And of course, you can just try to run summary to stop. Oh, summary is for the, okay, so for the object inside that results, okay. It's converged, okay, so it's loading, so we have uniqueness 19. So, yeah, so here, loadings for 76. Why 76? So actually we estimated 76 loading elements. So each element inside this huge matrix is unlike P by K. P is 19 by 4. Okay, 19 times 4. 19 times 4 is 76. So each element are estimated here. So we have number of loadings here and the uniqueness. Okay, this is the variance of the unique part. Okay, so we also have some functions. So this is the information of the object inside the function. Oh, obviously that is not good pattern. So we can try some orthogonal rotation method first. Okay, so if we change the rotation method to varimax, okay, varimax is orthogonal rotation method, trying to maximize the variance of the factor loadings. Then you can, highlight these two parts and run it again. Run it again. So you have another pattern. Okay. So the uniqueness are set here. So you have loadings. You can do some comparison. Okay. So actually, I have some slides prepared for you. So we have this is not for varimax. This is for varimax, the pattern of the factor loadings are shown here. So you can see, for example, the first row, okay, so visual is influenced by factor 2 largely, okay, 0.666, but also influenced by factor 1, 3, 4. But the loading, the coefficient is much smaller than the factor 2. So this pattern seems better than the previous pattern. And cubes, okay, influenced by these two factors, but the weight of factor 2 is much larger than the factor 1. And also we have paper largely influenced by factor 2, okay, instead of these three. And we have some general influence by factor 1. This is a coefficient, and these three are relatively small. You can see some patterns, for example, general, paragraph, sentence, word C, word M are largely influenced by factor 1, because these loadings are much larger than the other loadings. So this pattern is better than the previous one. And add, clearly it's not majorly influenced by factor 1. Actually, it is influenced by factor 4. And the code, again, it is not mainly influenced by factor 1. It is influenced by factor 4. But still, factor 3 has some large loadings. So counting also big. So it seems that these four are kind of like influenced by factor 4. And these 5 are influenced by mainly influenced by factor 1.
Yeah, is there like a rule of thumb with factor analyses of where cutoff should be, like 0.4?
That's a good question. That's a good question. We were gonna talk about that.
Okay.
Some people suggest 0.3. Some people even suggest 0.4. But usually people think that 0.3. 0.3 is kind of like a lot of people use that rule.
That's going to be the if it's 0.3 or more, then influence is good.
For example, some people. So for example, in this case, some people are going to decide, are we going to include this one or not? Because it's close to 0.4, it's larger than 0.3, or these two are quite close, not so, the difference is not so big, So that's why we're going to try different rotations. This is the first rotations, varimax, orthogonal. So we can do another rotation. Okay, so we're gonna try convex. Okay, let's try convex, and then we highlight this part again. So we have now it's much better than the previous one because here all of these are gone. As I mentioned, okay, these are actually all of these are numbers, but these numbers are tiny, so I'll just ignore them. So at least it's not shown here. So clearly we can see that these 4 are influenced by factor 2, and these 5, these 5 are influenced by this factor 1. But again, we have some loadings, and if you decide the cutoff point is 0.3 or 0.2, okay, whatever, all of this will be gone. So, okay, so this will not be here. And add these 4, so will be largely influenced by the factor 4. Yeah. Okay, so I have some pattern prepared for you. So this is the same thing. I think I miscopied here, so this one should go to that. Yeah, so I think I copied the result and paste in our slides. But looking at this lambda, this is a huge lambda matrix. This is a lambda matrix. We have 76 elements estimated here. And if you have this pattern, it's quite good because the red font, we clearly see that it's influenced by factor 2. And the green part, green test, clearly influenced by this factor 1. I put some gray color here, so that means you can just delete these numbers. You can just delete these factor loadings. And add code counting 3. This yellow tests are influenced by factor 4, but let me see, we have some
Straight,
yeah,
should bump over one.
yeah, so let me see, did I copy something wrong? Okay, so straight. Actually, you know what? I should use tab to move the 4, 8, 9 to, yeah, it should be here. Okay, it's here, like this. Like this. So, go back. So again, these 4 have very, very large loadings on factor 4. Okay, but here we still have quite a large number here. So that's why sometimes we need to rethink our questionnaire. So is this item truly influenced by these 2 factors? So you're gonna go back to check the item, the street. And the next, let me see, maybe I just missed the tab here. So figure, yeah, it should be have a space in front of the factor 1. Yeah, so that's much better. So these 5, or these are how many? 6, okay, are influenced by factor 3. Again, still here, okay, we have fig R, this loading, although it's less than the 0.5, but still it's quite large. And the negative 0.244, although it's less than 0.7, but still it's close to 0.3. So you're gonna decide what should we do. Basically, if we ignore those really small loadings, 0.1 or 0.2, so if you ignore those green loadings, I think, yeah, miss a tab here, fig R, let's see, fig R, yeah, if you delete those green numbers, then that's a final pattern. And based on this pattern, I still keep this number here. Okay? So based on this pattern, we can decide the red one. Okay, visual cube paper lavage. Okay, so it's influenced by factor 2. And the factor 2, by looking at these 4 tests, you can give a name, okay, find the common character of these 4 tests. It's actually the spatial ability. These 4 tests measure the spatial ability. And by looking at these 5 tests, we can give a name of this latent variable. So all of these are influenced by verbal ability. So we can name this factor as verbal. These 4 influenced by speech ability, or you can just simply say math ability, okay, or counting ability, okay, something like that. And these 6 are influenced by the memory ability. So that's how we decide these factors. So first step, number of factors is always very important. If we decided to use 3 or 5, you can still finally find some patterns, and you can do some explanation. So finally, the interpretation or the explanation should match your original design. So, or if you don't have some original design, then this should go to your theory. Okay, so you should have some idea about your test or your questionnaire. And finally, you're gonna make a story to make people believe that this is your latent factors. Okay. But sometimes if you decide, okay, 3 or 4 or 5, it's very hard to decide, okay, so it's 3 factors or 4 factors. So try to run the EFA and then try to combine similar terms. And then you can go back to, you can look at this result and you can go back to think about, okay, 3 more reasonable or 4 more reasonable or 5 more reasonable. Yeah, you're going to decide by combining the result and the background of your theory. Okay. But in this case, to me, okay, all of this makes a lot of sense. Okay, so I just believe that this is a 4-factor model. And here, yeah, let's look at this street. Here, sometimes we have some confusing results. Shall we keep this or keep this? Look at this number. This is even larger than this number. Okay, then we should go back to look at the street. Is this test truly test of factor 2, which is verbal ability, or test of factor 4, which is memory ability? So you're gonna look at this item, detailed item, and decide. Sometimes you're gonna decide if you're gonna keep this or not. If it's very confusing, that means this item is not well designed. Some people got confused. Is this for verbal test or is this for memory test? If it's really not good, you can just delete this item. Yeah, that's also doable. It's very common. Okay. If we delete this item, then the pattern is very, very clear. Okay. Yeah. So that's a lambda part. Okay, that's a lambda part. Yeah. And of course, we have some other information in the output. So for each factor, okay, factor 1, 2, 3, 4, we have SS loadings, some squares of loadings. This is because loadings are also estimates. Okay, those are estimates. And we have proportion, variance. Okay, cumulative variance. Okay, so each factor have this kind of like a proportion variance. So cumulative variance. So by adding these 2, we have this cumulative variance. By adding these 3, we have this cumulative. By adding this 4, we have this cumulative variance. All of these are common due to common factors, okay? Because these are factor 1, 2, 3, 4 are common factors, not unique factors. And unique factors, we have some variance here. Okay, so these are uniqueness. For 19 tests, okay, we have the specific, and we have factor correlations. So we have 1, 2, 3, 4. You can see that these factors are not independent because we use oblique rotation. So factors, these are 1, 1, 1, 1, 1, okay? Because it's a correlation matrix. So these off-diagonal elements are correlations among different factors. For example, factor 1 and 2. The correlation is 0.3. Factor 1 and 3. The correlation is 0.5. Okay? So these are not independent rotations. And we also have the chi-square test. We have demonstrated p-value. And by looking at the previous rotation, so we try to use Varimax first. Okay, Varimax is orthogonal rotation. So after you run the Varimax rotation, we have uniqueness, we have loadings. There's no correlation for factor matrix because that is just independent. It's identity matrix, okay? Because factors are independent, so the off-diagonal elements are 0. So that is not shown here, okay? The factor correlations is not shown in the orthogonal rotation method. But it's oblique, so we have to show what's the relationship among these factors. Okay, that's it. Yeah, so this is for oblique rotation. So this is notations or explanation of the R code. Okay, so we have the factor loading matrix, lambda matrix, we have communality. Remember that when we calculate communality, still remember, so we have an example. So the lambda times the transpose of lambda, the diagonal elements are just our communalities. Okay. So this is the amount of variabilities explained by common factors. In the previous examples, we have lambda matrix, and I said, okay, so you have to square each loadings and add them together. Actually, that calculation is just this case, because this is a matrix, okay? Matrix, transpose matrix, and row and the columns squared, and add them together. It's just this one. So the diagonal elements is just the communality. So communality, 1 minus the communality is a uniqueness. So we showed the uniqueness output. So this is a variance for the unique factors. So it's here. Yeah, so it's here. It's calculated as, okay, so lambda times the transpose of lambda. And the diagonal elements, okay, 1 minus diagonal elements, we have this 19 unique variance. And we also have SS loading, the sum of squares of factor loadings. Yeah, and the amount of variance explained by our factors. So we have already explained it here. And we have test. So we have test, okay. So the test of hypothesis that 4 factors are sufficient. The chi-square test is this number on the degrees freedom. The p-value is 0.4. So it's failed to reject X0. Okay, so 4 factors are sufficient. So we assume that there are 4 factors. So the model fits the data quite well. So we failed to reject the X0. So 4 factors are sufficient in our case. So that's R. And we can also use M plus to run EFA. So to conduct the EFA analysis. So M plus is quite simple, okay? So we have title, we have data. So all of these are default words. Okay, so title, data, variables, you cannot change this word. And also names. And after names, these are our column names in our original data because we have the original data, the huge data available. And then use variable. This is a subset of the previous columns, the previous data set. I'm gonna use the 19 tests only. Use variable inside of the EFA. I will not use all of this ID, female or grade. I'm not going to use all of this. Although these are available in our data set, but I'm gonna pick 19 tests here, okay, which are listed here to run the EFA. So names, original, all columns, use variables are use the variables inside our model, okay, use our variables. Analysis, okay, how are we going to run analysis? It's very simple. Type of your analysis. EFA. EFA is the type of your analysis. And then we have 1 and 4. What does that mean? Okay, so 1 is a minimum number of factors. 4 is the maximum number of factors inside this EFA. You can, so after you put 1 to 4, so actually you have 4 sets of results. The first set including 1 factor. The second set, okay, including 2 factors. And the third one, okay, it's 3 factors. The fourth one, the 4-factor model. And this, okay, these are comments. Okay, if we put this symbol here, that means our comments, so they will not run here. Of course, you can change this number. Okay, if you remove this symbol, the comment will be available, becomes available, so it will give you the new iteration numbers. Okay, this is really large iteration number. Sometimes, if you have very complicated model, you cannot get a convert result within the default iteration numbers. You can just change this number, okay? And you can take different rotation method. By default, by M plus, the rotation method is GeoMe. GeoMe is very good oblique rotation method. So you don't need to change other rotation method. But of course, it's available for you. If you really want to change different rotation, that's it, okay? And you can also look at the plot. So let's, this is the explanation, okay? Explanation of the code. Smallest number of factors, the largest number of factors are listed here after EFA, okay, after type equals EFA. So let's try to have the M plus here. Then you should be able to download the data file. Okay, so and the data file and the code. So the name is called EFA housing M plus. Okay, so that is our code. And the data file is called housing M plus.txt. Actually, it's the same data set, but we deleted the first row because the first row is the column information. In M plus, okay, the data file are just numbers. There's no characters, no letters. So we just deleted the first row to make it for M plus. Let's see, can I make it? Okay. So we have title, yeah, we cannot change this number, this word, okay. Data file, yeah, file is, so you can just also use equal sign, okay, file equals housing M plus.txt, it's the same thing, okay. So variables. So originally we have so many variables in our housing and plus TXC. All of these are available in the original file. And then we're gonna pick some tests among these columns. That's it. We have 19 tests available. And we have analysis type equal EFA 1, 2, 4. Some people say that, okay, why not just use 4? It's okay if you just, 4 that means, okay, it just run 4 factor analysis. So you can try to compare, okay, different factors, you can do some comparison. That's why we decided to want 4. Of course, you can also make it 5 or 6 or 7, okay, whatever. But actually 4 is decided that in the previous step, okay, we have decided the number of factors is 4. So you can highlight everything or you can just directly run. That's the result. Let me make it larger. So the first part is a repeat of input information. Okay, everything is repeated here. And then input reading terminated normally. So okay, the input information has been done. The next part is about our data information. So we have number of groups 1, number of observations 145, dependent variables 19. Okay, all of these are shown as our dependent variables because it's not like a regression. So all of these are indicators. We try to summarize, okay, we try to extract some latent variables from those indicators. So all of these are dependent variables. They kind of like a dependent variables. So we have 19. Number of independent variables 0 because this is for EFA. For EFA, there's no independent variables. Okay. Okay, so we have number of continuous latent variables 0. We're gonna decide the number of latent variables here by running the EFA. And those are observed dependent variables, 19 continuous tests. Okay. And estimator, maximum likelihood estimation method. Yeah, rotation here, geometry. Okay. In the code, look at the code. I didn't specify any rotation method. By default, the rotation in M plus is set as geometry. So it turns out it's really good rotation method. Okay. And the row standardization, okay, so the correlation matrix, gonna use that. Type of rotation, okay, it's oblique because it's geometry. Okay. Minimize the geometric mean of the load cell. And we have some other algorithm information, okay. Epsilon value, okay, information matrix, number of maximum iterations, convergence criterion. Okay, so these are algorithm information. This is our data set, okay. So input the data file, housing and plus dot. And again, these are explanation of our 619 tests. Okay, so these are descriptive statistics. Okay, variable sample size. Okay, this is a variable sample size, mean, variance, skewness, kurtosis, minimum, maximum, okay, percentage. Quantile, different quantiles, percentiles, yeah, median. For all 19 variables. And then we have model fit information. Yeah, we're gonna go back, we're gonna come back to this part later on. So we have 4-factor models. So 1 factor, 2 factor, 3 factor, 4 factor. Totally, we have 4 models here. So of course, number of parameters will be different. By changes of k, the number of factors, so the number of parameters will be different. Hassler values, illustrator values. Actually look at these p-values, okay? All of these 1, 2, 3, so these are significant. So, but for 4-factor, it's just not significant because the x0 means, okay, the hypothesis is sufficient or the factor models is sufficient or not. So here we have non-significant. And model compares. Okay, so we also do a lot of comparison. 1-factor, 2-factor, 2-factor, 3-factor, 3-factor, 4-factor. So the comparisons are all significant. Okay. 4-factor, 3-factor, 4-factors. So these two also have significant difference. Okay, because 3-factor is not enough, and 4-factors is also significant. Okay. And then we have result. Okay, so first part. Result of the EFA. So eigenvalues. So we have 19 eigenvalues. Okay, from the largest one, the one here, eigenvalue 1 to 19. From the largest one to the smallest one, 19 values. Then next part is the details of 4 models. The first model, EFA with 1-factor. Okay, we start from 1-factor and 2-factor, 3. Okay, this is the first set of our result. And we have model fit information, number of parameters, likelihood value, information criteria, okay, BIC, I-square. RMSEA, look at this. Okay, RMSEA is larger than 0.1. And the CFI, TLI, okay, it's much smaller than 1 here. This is for baseline, okay, this is for baseline model. SRMS, standardized RMSR is still larger than 0.1. And we have loading, okay, because we only have 1-factor, so that's it, 1-factor, everything. So this model assumes that all of these 19 tests just influenced by 1-factor, and that is lambda elements. Okay, so that's a result. And next part, we also have the estimated residuals. This is unique variance. Okay, so for each of these 19 tests, we have the variance due to the unique factors. Okay, we assume that there's only one common factor, so the rest part of unique factors. And we also have the standard deviation of this factor loadings. Those are standard deviations. Standard deviation of each residual variance. The T ratio, we have estimated value divided by the standard deviation. So the T ratio of this loading elements. T ratio of the residual variance. Okay, that's the end of the first set. Then we have the second set. We assume there are 2 factors. Okay, this is a 2-factor model. Okay, for model fit information, the number of free parameters, okay, likelihood value. RMSE, it's less than the previous one because the previous one is 0.12 something, okay, so it's larger than this value. But still, it's larger than 0.08, okay. And the CFI, TLI is larger than the previous numbers because previously we have 0.6 something, okay, 0.6. Now we have 0.8. It's larger than the previous model, but still it's less than 0.9. Okay. This number is again better than the first model, but still not good. And that is a pattern. Okay, we have 2-factor we have two factors, two latent factors. So we have two columns, and it seems that the virtual are more influenced by factor 2 instead of factor 1. Okay, cubes are more influenced by factor 2 instead of factor 1. Then for paper, okay, for general, it seems that it's more influenced by factor 1 instead of factor 2. Okay. So that's a lambda matrix. It's a lambda matrix. And we have the correlation because now we have two factors because oblique. Okay, this is a correlation between factor 1 and factor 2. And the residual variance, the unique variances, okay, and standard errors for these factor loadings. And standard errors, okay, for all of these unique variances. T ratio, ratios for unique variance. Okay, now let's look at the third set. Okay, EFA with three factors. Model fit. You can also compare the EIC, BIC values. Okay, so we have different sets. You can just copy these numbers, okay, from first set, second set, third set, okay. Fourth set, you can do some comparison. This value is much smaller than the second set. Okay, now it's quite close to 0.05. Still larger than 0.05, okay, but smaller than 0.08. And this value is larger than the previous set, okay, so larger than those values in the previous two-factor model. And also this one is quite close to 0.05. And we have lambda. This is a lambda. Now we have three factors. So we have three factors. And correlation, okay, correlations between factor 1 and factor 2, correlations between 1 and 3, 2 and 3. The residual part, the standard error part, the standard error for the residual, T ratio. And finally, we have these four sets. Okay, EFA with four factors. Model fit information, technical values, definition, EIC, BIC. Now the p-value is not significant. Okay? I'm checking the previous result. Okay? This is three-factor model. The p-value is significant. Okay? Oh, no, I'm sorry, this is for baseline. Let's look at the, okay, here, okay, yeah, again, this is for the current model. Current model, the p-value is significant. But for the full model, for the four-factor model, yeah, here, this is not significant. P-value of the chi-square value is not significant. And then let's look at this RMSE. It's quite small. It's very close to 0. It's 0.025, much smaller than the third test, the three-factor model. And these numbers are very close to 1. Okay, it's very good. It's 0.991 and 0.984. And also this number is very small, very close to 1, close to 0. And that is a pattern. Okay, this is a pattern. This is a pattern. We have four factors, 1, 2, 3, 4. And if you ignore those small numbers, okay, all of these are very, very small numbers. 0.0, some number, okay, 0.0 and also 0.1 or 0.19. Yeah, if you look at this, okay, so this is the largest one, this one is still quite large, but if you use a cutoff point, point 2, you can ignore the third one. Yeah, and also here, this is 0.3, factor 0.3, this is 0.8, okay? So this pattern is different as the previous in R. What did we use? I forgot which one did we use for rotation? Promax, okay? So in R, we use Promax, but in M plus, we use GeoMe. If you compare the lambda matrix, you will figure out they are different. By using different rotation method, all of these lambda elements will be different. Just pick one method you think that is going to help you to explain the factor models, okay? So this is the GeoMe result. But the majority information, yeah.
But the GeoMe and the Promax are both oblique, right?
Yes,
Okay.
but they are different. Both are oblique, but they are different. Yeah. So you can just pick by using the Promax or by using the GeoMe. Yeah, you're gonna pick your favorite rotation method. Yeah. It seems that this one is not clearer than the Promax because when you look at some values here, they are quite close. And also, yeah, this is smaller than this one. Yeah, maybe Promax, yeah, Promax is much better than this method. In this case, for different case, it may have different preferred rotation. Okay, for this data set, maybe Promax is better than the GeoMe rotation method. And we have the correlation matrix. Yeah, this is the correlation matrix of this 4 by 4. Yeah, so we have 4 factors. So these are correlations. We also have the residual part, the residual variance. Standard error. Standard error for the residual part. Ratio for all of these. Okay, so finally we have the end of this estimate. Okay. So it's eigen decomposition. Okay, so we can just use diagram. Okay, so these buttons are great. Maybe we didn't buy the package. So see. Okay, so this is just eigen decomposition. Okay, it's not under the diagram. It's on the plot and the view plots. Okay, yeah, thank you. Yeah. Actually, we have already plotted it by using our R code, but M plus can also help us to do that. Okay. And we have some other options. Okay, that's it. That's for our M plus code. That's it. We have already finished R and M plus. So this is your homework. Okay, so homework. Please write out the meaning of each line of R code and M plus code. Okay, that I provided. So I have the M plus code here. You can ignore this part, okay? These are our options I provided you to change your code, but this is not necessary. If you don't want to change the default setting, you can just ignore this part, okay? And the R code, I give you a lot of R code, so you can, let me see. So in the R studio, if you don't really want to talk about the parallel analysis inside these functions, then that's okay. You can ignore this part, okay? So this is not very, this is although this part is important, but this is not required. Okay, so because it involves some other very powerful functions, a lot of like. It's up to you. If you really want to count this part, it's okay. But if you ignore this part, I will not just pick up. It will stop me. But the other parts are important. The other parts, both parts are important because later on, if you want to use this EFA, you can understand the meaning of this commands. So, any question for EFA? And it's due next Monday. Okay. Any question for this part? Good. Let's have a break. Okay. 15 minutes break, and then we're gonna move forward to CFA. Good, thank you. Sometimes we can just do the test. For example, some factors are truly influence some indicators. Is that 0 or not? Okay, we can just do the test. Or these two factor buildings are the same or not? These two indicators are equally influenced by that factor or not? And we can also test a relationship between two or more factor loadings. Okay, what's the relationship? And test whether a set of factors are correlated or uncorrelated. All of these can be finished, can be tested by running the CFA. Before we run CFA, I have to explain the model identification. As I mentioned before, so if let me just give you the review of our factor model. So we have so we have a lot of like factors. So we have lambda, we have factor. Suppose we have K here. Okay, K is from 1 to capital K. We have IJ here. Okay, so we have this is for I. This is for G. And we have some areas. So all of these are unknown. Okay, factor loadings. We need to figure out what's a lambda factor loadings. We need to know these factors. So only we have the observed variables available. So we only have this information, but we need to figure out a lot of like also the variance part here. Okay. A lot of like unknown factors involved here. If we do not identify some value here, it's very hard to get the fixed value. For example, if you think about 7 is 2 plus 5. Okay, 7 also is 3 plus 4. If you do not somewhat identify, okay, or if you don't put some anchor on this side, there's a lot of solutions. Okay, so we need to fix some part here, and then we can have a solution. Okay, we have so many possibilities to have the 7 result here. So if you think about the y's are known, 7 is known, but all of these parts are unknown, we need to fix some part of the solution, and then we will have a unique solution. So that's the logic. So we can just do some part of the model identification like this. We can fix one non-zero loading at 1. So we have a lot of loadings. Okay, we have a lot of lambdas. So we can just choose one non-zero loading and fix it at some value. Usually, we assume that we fix at 1 because it's gonna simplify our case. Of course, if you want to fix at 2 or 3 or 100, it's totally fine. once you fix that part, we can get the estimate of the other part, okay? Or you can fix the factor variance at some specific value, and usually we assume it's 1. Okay, that's another way. Usually we have two ways. Either fix one non-zero factor loading at some specific value, usually at 1, or we fix some factor variance at some specific value, usually at 1. Okay. If we have the path diagram, then this is the first case. Okay. So we have 3 observed variables here, y1, y2, y3. We assume it influenced by the common factor f here. So all of these are lambda, okay, these are lambda. Assume this one is not 0, okay, not 0. Then we're gonna fix this path loading at some value. Say it's 1, okay. Once you fix this part, it kind of like put some scale between the observed value and the latent factors. So latent factors has some scale. Because what does that mean? If this means 1, so if I increase 1 unit of this latent factor, so the observed y1 will increase by 1 unit. So it's kind of like a fix the value of this kind of like latent variable. This is latent, this is unobserved. So the unit kind of like a fixed, same as the unit of the y1. So something has been fixed. And then based on this information, we can estimate the lambda 2, lambda 3, and the lambda 2 and the lambda 3 can compare with this 1, okay? So it's larger than 1, okay, or it's smaller than 1. This is one way. So we fix one non-zero loading at 1. We can also do this. Okay, so here I didn't put so the variance of f. Okay, so it should be the variance of f. The variance of f fixed at 1. Then we also fix something here. Okay, the variance of the latent factor has been fixed 1. Then this information can be freely estimated. So I don't care about this lambda 1, lambda 2. Okay, so based on the variance of f, we can do further estimation of the actual lambda value. Okay, so either by using this method or by fixing the variance of the latent variable f at 1, we do the model identification. But you have to choose one. Okay, you have to identify a model by either fixing lambda at 1 or variance of factor at 1. Yeah, so I prepared some questions for you. What is the difference between them? So the difference is, yeah. So actually, this should be. So it should be the variance. Fix it at 1. Okay. Needed to delete this part. Okay. So what's the difference between them? So yeah, of course, the difference is this is like the loading fixed. This is a variance fixed. Okay. What are the degrees of freedom? Let's check the first model identification. We talked a lot about the degrees of freedom. So how are we going to calculate the degrees of freedom? First, let's check the number of information. Suppose we have 3 observed variables. So P is 3. What is the number of information? number of information. 3 times 4 divided by 2 is 6, right? So we have 6 pieces of information. 6 pieces of information available for us to do the model estimation. So the maximum, the total number of parameters should be 6. We cannot estimate 7 or 8 parameters because this is the total possible information we can have if we have three variables. Then what is the number of parameters? Number of parameters, okay, not a P, okay, parameters. In this case, okay, so we need, this one has been fixed, so we don't need to do any estimation here, okay. So we need to know number 2, number 3, variance of F, okay, this is one parameter. Also 3 residuals, okay, residual, variance of the residual of Y1, variance of the residual of Y2, or the unique factors, okay, unique factors. So what is the number of parameters in this case? What is the number of parameters? 6, that's it. Number of parameters, 6. The total information, the maximum number of information here with 3 independent variables, 3 variables is 6. We're gonna estimate 6 parameters, that's it. We cannot estimate one more parameter, for example, number 1. It's not allowed because if you want to really estimate all of these, then you will have 7 pieces of 7 parameters. That's not allowed for this model. You have to identify something. You have to fix something. In this case, this number 1 is fixed at 1. Okay. So degrees freedom. What is the degrees freedom in this case for the first pass diagram? 0. Yeah, 0. It's saturated model. Okay. We don't have any information available in this case. That's it. 6. Now, okay. Let's look at this case. 3 P, okay, the same 3P. So the number of information again is 6, okay? So maximum. In total, we can estimate 6 parameters. Now let's look at the number of parameters in this case, number of parameters. We have lambda 1, lambda 2, lambda 3. All of these factor loadings need to be estimated. We have variance of E1, E2, E3. Okay, variance. This one is fixed, so I don't need to estimate the variance of F. That's it. Again, in this case, the number of parameters is 6. 6, that's it. I cannot estimate more parameters in this model. 6 is the maximum number. So degrees freedom is 0. So this is another way to understand that we have to fix something to identify our model. Otherwise, it's not doable. Otherwise, it's beyond our ability. We only have 6 pieces of information here.
What is the number of information, please?
Oh, okay. So yeah, you didn't take the SEM one. So they have formula. Okay, we have formula. So if you have P is the number of information, I'm sorry, P is the number of variables. Okay, so where's the? Yeah,
I can look at it.
Okay, yeah,
I can just look it up.
Okay, yeah. If P is the number of variables, in this case we have 3 variables. Then the number of information is calculated P times P plus 1 divided by 2. This is the formula.
Okay.
Yeah. So if P is 1, what does that mean? Only one variable available, just X, or just Y, just one variable available. Based on this formula, okay, P is 1, the number of information is just 1. We can estimate 1 parameter, that's it, because we only have 1 variable. If P is 2, yeah, that's P is 1. If P is 2, based from this formula is 3. Okay, number of information is 3. Okay, so if you have two variables, x and y together, then you have variance of x available, you have variance of y available, you also have covariance of x and y available. So you have 3 pieces of information. You can estimate the 3 parameters in total, okay? Yeah, that's the formula. Okay. So we have, yeah, why do we care so much about the freedom? Because freedom is so important. You know, involves model parameter estimation, okay, model structure, path diagram, model identification, sample size. Yeah, so all of these will, yeah. Degree freedom is important in our model estimation. Okay, next, let's look at a detailed example. So we use the same example, we use the same data set. We choose 19 tests among, 24 tests, and we try to have this, figure out these 4 latent cognitive abilities. So 4 domains. By running the R code or M+ code, by running the EFA, we figure out that the K is 4, and we have this pattern. Okay, 4 tests for spatial, 5 tests for verbal, 4 tests for speed, and 6 tests for memory. So that's our vector model after we run EFA. Now, I'm gonna have this model to do the test. Okay, so suppose this is our existing model, or this is our hypothesized model. So based on the result from EFA, what is the path diagram? Now the path diagram is not same as EFA. For EFA, we don't have any existing model. Okay, so for EFA, we just try to estimate each factor loadings and to see if it's big enough for us to keep that. Because for CFA, I have already got this pattern, this vector structure. I only need to follow that structure to write out to have the path diagram. So basically, we have 4 tests. Okay, we have 4 tests which are influenced by our spatial, and we have 5 tests. 5 tests for verbal thing. And we have speed test. Okay, this is for speed. This is spatial. So we have, I think we have 4. And we have memory 6. So this is our path diagram. And of course, among these factors, they are correlated because this is a oblique notation. And of course, we have some unique variance. Okay, so we have unique variance for example, U1. Okay, we have U2, the variance for U2. Is 19 tests. All of these are, we can just finish this. This is the path diagram for our CFA. If you want to fill out the space and just, the visual section tests and cubes and the filter form boards. So we're gonna fill out all of this. Okay, this is the counting and the streets. Now, let's run CFA. This is our past diagram. How are we going to run CFA in R? Okay, past diagram here. CFA. Remember that in SEM1, we learned the SEM package. So, I will not cover the review of the SEM package. So let's just try to look at the code. Okay, so let's go back to the R Studio. So you're gonna open the R Studio and download the code named CFA.R. Okay, so the code is called CFA.R. That's here. And of course, you're gonna prepare your data, make your data ready. So reading your data here. To the beginning part. Okay. Beginning part. Now let's have the SEM code. It's SEM package. If you haven't installed that package, you should, okay, so here, the right panel, the bottom part, there's a package. There's a button called package, okay, package. And then you're gonna check if the SEM package is available in your computer, in your desktop, okay? So you're gonna check if SEM is available or not. If, here, okay, I got it that, okay. I found that the SEM is available. So if you don't have this package, you should use an install package or just click, okay, click here. This is install, and then tell R what kind of like package you want to install. So SEM support, okay, then click install. So it will just do the installation for you. But in my computer, it's already, so I can only check. Okay, so here in front of this package, I can check this package. Or you can manually type in library SEM to make this package available for you. Next, we're gonna run a lot of like functions inside this package. So either by typing library SEM, just like we did here, or you can just check the package in the RStudio, either way. And then we're gonna specify our SEM model. So this step, I believe that if you took SEM1, so this step should be very familiar for you. Each of you should be very familiar with this code. Okay, so basically, we just figure out the structure, the path diagram of our CFA. So let's look at the beginning part. Okay, this is the name of my CFA model. This is model 1 because you're gonna run a lot of other models. So suppose this is model 1 CFA. Again, you can change this name. This is just a name. And by using the function inside the SEM package called, okay, so specify model, and then parentheses. Inside this part is description of your model. So each line include one parameter. So for example, here, this is a statement to describe the lambda 1. Lambda 1 So, suppose we have name, okay, spatial to visual one. So the visual one, spatial. Suppose this is named lambda one, okay, so we have lambda one here. And the lambda two, spatial to cubes, okay, so lambda two. So all of these lambdas have, all of these have their names, okay, so we have a lot of lambdas. We have three parts inside this code, okay, so let's have a brief review. So the first part tells us the path, so from which variable to which variable. So usually this is a latent variable, okay, and go to the visual. So that means the spatial, that means the spatial ability gonna inference, okay, goes to inference the visual item here. And the name is called lambda one. This is the name of the parameter. And the starting value, NA, so the system will decide the starting values for us. So you don't need to specify any starting value, but in some special case, if the model does not converge, then you can just try to put some numbers here to use the starting values. But in many cases, it's just NA. You can continue, okay? Continue lambda 2 to lambda 3, lambda 4, okay? All of these are lambda values. We're going to have 19 lambda values because we don't allow cross-loading. So that's why. For simplified CFA, we don't have any cross-loading. So each indicators are influenced by one latent factor. So we have 19 tests, we have 19 lambda factor loading. So this is lambda 19, okay? This is lambda 18. So we have all of this described here. And then we have the correlation among these factors. Spatial factor, this is a latent factor, and the verbal latent factor, R12. Spatial verbal, the correlation between these two factors, R12. This is another parameter we needed to estimate. And we have spatial speed, R13. Spatial speed, okay, this parameter, this correlation is named R13. And we have R14, spatial to memory, this is R14. R23, okay, verbal and speed. R23. R34. Okay, we have so. Oh, we also have R14. Okay, R24. Yeah. So we have their correlations among factors because it's not orthogonal rotation, it's oblique. So we have their correlation. And then here, let's look at 48. Okay, let's look at this row. It looks something different. Spatial. This is a variance of spatial, okay? Variance of the spatial variable, okay, within the factor, okay? This variance of spatial probability. What does that mean? I don't want to give any number or name of this parameter because this parameter is not a parameter. This has been fixed at 1. So I fix the variance of the factor of spatial at 1. This is the value of the fixed value, okay, NA. I do not want to estimate this parameter. This one is gone, okay, this one is fixed. So this is fixed at 1. Also, I'm gonna fix all of these latent, the variance of this latent factor at 1, okay. So all of this has been fixed. So one of these 4-factor variance has been fixed at 1. And let's look at this part, okay? What are these? Visual. This is all, again, variance. But these are not factors. These are visual are items. These are tests. detailed test. This is a residual variance, okay? This is a variance of the residual of visual test, and I name it S1. So S1 should be estimated. Starting value is an A, so it's this value, okay? This value, this is a S1. S1. This is a variance of the residual of the visual item, visual test. And of course, we have S2, so we're gonna have 19. We're gonna have 19 S. Okay, so figure to figure, okay, figure W to figure W S19. So this is our model. This is our model. So we end this model by using the point sign. You have to do that. Otherwise, the R will just keep asking you, what's your next information? What's your next model? So highlight this part together, and just run. And then we're gonna run SEM. Okay, SEM is a function inside of the SEM package. We need to tell the model. This is our model we just specified here. This is a covariance matrix. You have to use a covariance matrix. Where's the information here? That's it. Okay, covariance matrix is created here. Here we have your data ready. Okay. COV, covariance matrix of your data file. We just name it FA covariance. Okay, FA covariance here. So you make it ready, FA covariance. And also sample size. Sample size should be imported by using the SEM package. And it's here. Sample size is a number of rows of this vector of this data set. So N is here. So everything's ready. So we're gonna run this part, covariance matrix, and then just run the SEM. Okay, all of this information is ready. Run the FA. But if we just directly run the SEM without the options of the fit indexes, sometimes we just have very, very few information. Okay, so suppose if you just run the simplified SEM. So for the model fit indexes part, it's just that, okay? So you can use the option to open the model fit indexes. And run again. So now you have a bunch of model fit indexes available, because you made that open, you made that option open. So only one summary. We have model cluster variable freedom, okay, value, the bonus, okay, GFI, HFI, RMSEA, the RFI. Yeah, so these are model fit indexes. And also we have the R square, yeah, for endogenous variables. Parameter estimates. Okay, this is a lambda. Okay, these are parameter estimates. So let me lambda from lambda 1, lambda 2 to lambda 19. Those are factor loadings. Okay, so from here to here, these are from here to lambda 19. These are factor loadings. So we have the estimate of this lambda, and we have standard error, we have the z value or the t ratio. Okay, anyway, it's a ratio of these two numbers. And then we have the correlation among these factors. 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, okay, 3, 2. These are 6 covariances among these latent factors.
And then we have the residual variables, okay, from S1 to S19. We have this, residual variables, okay? Yeah, everything I reported here. That's a factor, parameter estimates. And yeah, actually this column should go to the column here, but because the font is so big and the space is so limited, so we just reported it into two parts. This should go to the p-value of each of these. Okay? P-value. And number of calculations is 25. Yeah, that's it. That's all for SEM result. So you should be able to understand each command there. Okay? So we use a specified model in the SEM package. But you can see that the structure is very clear, but it also has some disadvantages. You have to put all these parameters in our code. It just, if you have really complicated models, so the code is really long, okay? Then let's try a new package called Lavant to try to simplify the code. So if you haven't installed the package, the first step, gonna install the Lavant package. Yeah, that's it. Two ways you can use a menu. You can type in this part, okay, install the package Lavant inside the R code, or you can use the RStudio. Okay. Yeah, or you can just use the RStudio to install the package here. Click the package install and the Lavant. Okay. L-A-V-A-A-N. Okay, Lavant. And I think I have already installed it here, so I don't need to repeat it again. So if you have this package available, then just check the available. Yeah. But before that, you're gonna uncheck SEM, because previously you have SEM installed. SEM and the Lavant packages are running with SEM. Okay, so some functions are shared by these two packages together. So if you use both, so there's a conflict. So if you use the library of these both packages, sometimes you have some errors. You got some errors which is very weird errors. So I suggest you to uncheck the SEM. Okay, uncheck SEM. Or you can just type in detach. Okay, detach the package of SEM. And then attach the Lavant package to make sure that you just use one package at the same time. Okay, you cannot just run these two at the same time. Otherwise, yes, sometimes you have some very weird errors. Okay, just detach and the library, or you can just check. Okay, the one and uncheck SEM. Okay. Now, let's look at our code. This is a model in Lavant package. We don't need to specify lambda 1 to lambda 19, okay, S1 and to S19, a lot of R. That's it. This is our model. This is our CFA model. I have 4 latent vectors: spatial, verbal, speed, memory. Each vector, okay, each of these 4 factors are measured by these tests. These are items or tests. Spatial equal tilde. Okay, equal tilde means, okay, that is measured by these tests. Equal tilde, visual cubes, paper, lasagne. These are 4 tests. That's it. And verbal equal tilde, general, paragraph, okay, sentence, word C, word F. That's it. And we have speed 4 tests. We have memory 6 tests. Okay, 1, 2, 3, 4, 5, 6. Okay, so we're gonna continue here. That's something here.
Yeah, question?
With that model, is it already, does the package, when you have the CFA model, is it already, putting in a rotation for you?
This is the second step. This is not EFA. EFA, we consider rotation. For CFA, no rotation.
Okay, that makes sense, right?
Yeah.
It's already modeled.
Once you got the final pattern of the factor model, that's it.
Okay.
Yeah, rotation just for EFA. This is for CFA. Great question. Yeah, thank you. So finally, we decide this is our model. So we have, we have this structure, factor structure. That's it. Four lines. It automatically, the function will, of course, you have to run the CFA, but this is a function to use. This is just a model, okay? Automatically, they will just estimate the residual, okay, the factor loadings, all of the factor loadings, and the correlations among these factors. Okay. So you can just, again, you're gonna highlight these blocks together because this is just one model, okay? Code, and highlight this part and run it together. And then you have your model ready. This is your model. Next, there's a function called CFA inside the Lavon package, okay? Lavon package. In SEM, this is called SEM. In Lavon package, we have CFA. CFA, this is your model. This is your model. You just define your model here. What's your data? The data is a factor FA data, small set of the whole original data. You don't need to care about the covariance matrix. You don't need to care about the sample size because automatically they will just calculate those information for you. So the data information, the model information here, two parts. That's it. And the results are saved here. Okay, this is the results. And then you can use a summary and fit measures. Yeah, you can tell us the model fit indexes. Okay, so you can use this function to check the result. Okay, just check summary first. And highlight wrong. Now you have the result available for you. Number of iteration 256, okay, and estimated maximum likelihood estimation, and this is an optimized method. This is algorithm part, okay. Number of model parameters 44. Okay. Why 44? You can calculate. Okay, we have 19 lambda values, 19 residual variance, and we have 6 correlations. Correlation among different factors. So 19 plus 19 plus 6, totally we have 44 parameters. 44 is our number of parameters, yeah. And the number of observations, okay. And yeah, you can also calculate the degrees freedom here, okay. And the parameter estimate. These are information of the algorithm and the data file, and then okay, now this is an estimate. Okay, so we have spatial. We have 4 tests: visual, cube, Smith, paper, design. Okay, the lambda coefficient are provided here. By default, in the code, I didn't do any model identification, but the code choose one method of model identification for you. They fix the first non-zero factor loading at 1. This is their default way to identify your model. Of course, you can change it. You can use the other model identification. But by default, this one fixed at 1, so we don't have any information available here. You don't need to do any estimation, okay? So all of these are flat, okay? And then this is a lambda cube, okay? As standard error, z-value, probability. This is lambda 3, okay? Lambda 4. Same thing for the verbal sets. The first non-zero factor loading has been fixed at 1. And then we have the other lambda the speed, okay? This one has fixed at 1. Okay? And memory, okay? The first non-zero factor loading has been fixed at 1. To identify your model, okay? And the other 5 lambdas are estimated by the model. Lambda, okay, lambda value here, okay. And the covariances. These are covariances among different factors, okay. Spatial verbal, okay, that's it. Spatial speed, that's it. Spatial memory, that's it. Okay, all of these are covariances. Covariances among different factors. Verbal speed, verbal memory, speed memory. And we also have variances, okay. These are variance of the residual of these 19 tests, okay, from here to here. Residual cubes. The variance of the residual of these 19 tests. Estimated scenario z-value probability. But we do have some factors, okay? These are 4 factors. Because we have already fixed the first non-zero factor loading at 1, so these factor variances should be freely estimated. You're gonna pick one. If you choose that one, fix it wrong, then you should provide the estimate of the variance of the factor. If you, the other method, you can also fix the variance of these 4 factors at 1. Then those factor loadings should be provided. So you should choose one method, okay? So if we fix the factor loading at 1, these 4 values should be provided. So the variance, the standard errors, the z values, the p value. That's it. These are model results. We can also check the indexes.
I have a question.
Yes.
Then for the interpretation, when you go to the latent variable and they're less than 0.05, is that basically saying then for the cubes, paper, and lozenges for spatial that those items confirm?
Oh, which part? Let me go back to, you mean the lambda part? So
Yeah,
which
the latent variables or the rules and
let me
that.
see. This is for SEM.
Okay, so
Yeah.
so here, how do we,
Yeah.
so would you be interpreting each
Okay.
one?
Yeah, so that means if in this way, actually we fix the unit of the latent variable. If we change one unit of spatial abilities, the visual test will increase by 1 point. After you fix the unit of the spatial, then that means, okay, if you increase 1 unit of spatial abilities, the cube test will have 1.445 points higher. If you increase 1 unit of spatial ability, then the paper test will have 0.32 points higher.
Okay, so the probability, the 0.000 doesn't mean that these items measured spatial then. This is more.
It's coefficient. Think about the coefficient. Think about the slope.
Right, it's a
Slope.
Okay.
It's just, yeah, think about the lambda. The lambda, where's the lambda? These are just coefficient. These gonna influence the outcome here. So the coefficient, the factor loading tells us, okay, if I change the latent ability, what's the change in the item test? Okay. Yeah. It's just like a B, the coefficient B. But the problem is that the independent variable here is latent. It's a factor, it's latent, not just like the independent variable are observed in our regression case. And let's look at this case. Okay, if I increase 1 unit of spatial, then the losange will have 1.177 points higher than, yeah. The same thing for the rest of coefficients. Yeah. Now here, if we type the fit,
measures of this result. Okay, this is the result. Fit measures is a function inside of the Lagrange package. Then we're gonna see a lot of like fit indexes here. Yeah, all of this is huge. Okay, there are a lot of like fit measures are reported here. Some of them I don't know what's that. Okay, so this is number of parameters. Okay, 44 number of parameters. What is FN? Yeah, we need to check the details of this function. High-square value, this figure 146, p-value, baseline high-square, baseline degree student, baseline, all of this baseline. You can just, yeah, see it, CFI value, FI, PLI, FI, yeah, FI, so, all of these model-fit indexes are provided here. AIC, okay. This is sample size, okay, and total sample size here. And RMSEA, okay, RMSEA is quite close to 0.05. Lower bound, upper bound, okay, RMSEA, lower bound, upper bound. Value. OMR, so yeah, we put a lot of like information here. GFI, EGFI, MFI. So that's method by fixing factor loading at 1. So if you're trying to use another model identification method, if you're trying to fix the variance of latent factors, spatial, speed, or memory, or verbal at 1, then you can use this method. Again, CFA, the same function, the model, the same model here, okay, the same data here, but now I'm gonna change some option here. Standardize the latent variable at 2, okay, 2. In this way, the latent variable, the variance of the latent variable will be 1, fixed at 1, and the factor loadings of lambda 1, lambda, or the lambdas will be freely estimated. And you can try, yeah, highlight this part. Now, yeah, let's look at the result. All of these variance of these latent factors are fixed at 1. Spatial, verbal, speed, and memory. And we don't have anything else because it's fixed. These are not parameters. And we have the residual variance, the same thing here. And let's look at the lambda part. All the lambda values are reported here. Yeah, here. All of these lambdas are reported here. Now it's kind of like we change the unit, we change the scale. We assume, in this way, we assume the variance of the spatial is 1. So all of these factor loadings are different. Of course, the meaning is the same. If you check the p-value, they are exactly the same, okay? But the reported values are different. So that means, okay, if I change 1 unit of the spatial ability, the visual test will have 4.763 points higher. Again, Hubris is 2 point something. Okay, the paper is 1 point something. Okay, Los Angeles is 5 point something. The scale is still the same, but we change the unit of the scale. If you do the comparison, okay, if you change it to 1, if you rescale this number at 1, then still have this is like a 0.4 something, this is 0.7 something, this is 1.17 something. But they just change the scale. The meaning is the same, but the actual numbers are different. Okay. And the same for the verbal ability, speed ability, memory ability, covariance. Yeah, we also have the covariance among these. factors and residual variances. Again, if you run the fit measures exactly the same. Okay, so if you run, because these two models are identical. The only difference is just we use different units to explain these two models. The scales are different, but the results are the same. Okay? So if you run the fit measures, all of these are exactly the same. Okay? Yeah, 44 number of parameters, aspect value, okay. Illustrator, minus here, the same value here, all of these results are the same. The only difference is the scale of the calculating part. Yeah, we change the scale. Okay, we change the scale. Yeah, so this is our code in our one package. Really simple. We just model specified here. And then we can see a few functions. This is an explanation of the previous code. So use an equal sign builder plus builder to say that is a measure. That is a measurement quantity. So before we start, so for example, in this case, spatial variable, because spatial is not existed in the data file. This time it's not existent. So we create this variable by using this is a variable just the box, just waiting. So this simple after a lot of the last one. One and then next Here's the option for you to identify model. Choose so that is the best option. This is the method. It's in the system. Loading it. Yes. If you choose the scale, divided by 4.7 of all of these all numbers of here divided by 4.763, so we will have these numbers. If you divide all of these numbers by 9.385, then like the semaphore user. And that is a covariance field comparison. Covariance. Yeah. The actual numbers are different because the scales are different. Covariance is. Now let's look at the variance of the residual part. Okay, this part is exactly the same.
Variance of the residual visual, 24.788. Variance of the residual of the visual, 24.788. Okay, these parts are exactly the same, although we use different model identification method. But not this part, okay, this is a fixed at 1. But here, we have 3 estimates, okay, we have a lot of 4 estimates here. Yeah, so this is we did the comparison between the package, and we also evaluate, or we also do some evaluate our model. Okay, we have a lot of like model fit indexes reported by running the fit measures. So now it's 8. Okay, we're gonna finish today's slides. Okay, so I'm gonna finish CFA and M plus in 5 minutes. Okay, so the same thing. Title, we have data, we have variables, original variables, a lot of variables, use variables, just 19 variables. And then the model, inside the model, we define our CFA. It's kind of like a Lavon package. So we have spatial by these 4 tests. Okay, so in the one package, we use equal sign tilde, and we have plus sign to connect these 4. In M plus, we use keyword by. Remember, we have different keywords in M plus. By means measured by, is measured by. Some variable, latent variables created, newly created, and is measured by some tests. That's a syntax of M plus. Variable is a newly created new variable. This variable is measured by these 5 tests. Speed is measured by 4 tests. Memory is measured by 6 tests. That's it. This is for M plus. And again, this is model identification. So if you use this way, the first vector loading will be fixed at 1. Fixed at 1, fixed at 1, fixed at 1. If you don't want to use this method, then you're gonna add a small star here, okay? So that means I'm gonna freeze the default setting by fixing the vector loading at 1. I'm gonna freeze that setting. Instead, I'm gonna fix the spatial variance at 1. The variance of the variable, latent variable at 1. The latent variable speed. Okay, so variance fixed at 1. Variance fixed at 1. So this is another way to identify your model. All of these, the vector loadings will be freely estimated. The default setting will be freed. Instead, I use this way to fix the variance of the latent factors. So these 2 codes are exactly the same. Just 2 ways to identify a model. Okay, just like the one package. If you put in true or false of this option, okay, 2 methods to identify a model. Yeah, either this way or this way. So in M plus, you can also download the code from ELC, and let's just quickly run the results. Okay. So this is M plus. It's called CFA1, CFA2. Okay, 2 methods to identify your model. CFA1, CFA2. This is the first method. Yeah, just run, then the results are reported here. We're gonna cover the result. We're gonna look at the result next week. Okay, we don't have any time now. And for CFA2. So CFA2, just another way to identify your model. Okay, this is another way to identify your model. So click run, you have the results reported here. Okay, that's it. That's for today's class. And let me see. Yeah, if you have emails, then Immerse, you don't need to do any coding. Okay, just draw this tag diagram automatically, then we will just estimate all of these parameters here. Okay, this is summary. Okay, summary for EFA, for CFA. For EFA, you have to decide the number of factors, your main methods. Okay, then run factor analysis, try orthogonal rotations, try oblique rotations, compare models. Okay, based on your literature, also based on your data, you're gonna do some decision. Adjust your factor model. Sometimes you're gonna delete some items and rerun your model. Adjust your factor model, rerun factor analysis, and give a name of your latent factors. That's for EFA. For CFA, you're gonna specify a model and just identify a model. Identify a model, run CFA, evaluate your model fit. Is that good or not? And then do the interpretation. So those are steps for EFA and CFA. That's it. Okay. So homework 2. Homework 2 is due next week. Okay, homework 2. Yeah. Just do the explanation of the R code and the M code. Not for CFA. Because that's too much. Okay, just for the previous part, for EFA part. And you will have new homework 3. Run EFA and CFA for your actual data set. I will give you a data set. Okay, that's for homework 3 and homework 4. Okay, yeah. Okay, that's it. Here, yeah, let me just turn off.